Hello everyone. In this video we are going to look at a problem for kinetics of particles, and we are going to use the Cartesian coordinates. So here you have two blocks on the top of each other. Mass of A is 15, mass of B is 30 kilogram. Mu S and mu K are given by 0.4 and 0.35. There is friction between B and the ground and between A and B. We apply a force to the bottom block B, one time 200, the other time 400. You want to find the acceleration of the blocks, right? The acceleration of each block for case A and for case B. So, as you know, the first step after reading over the problem and writing down whatever the problem is giving to us and whatever is being asked, correct? So here the unknowns are clearly A, and AB. And by A, we mean only the X component, correct? Because the Y here is going to be 0. So these are the unknowns of the problem. And you know, we have two objects with masses, so we can draw two FBDs, one for block A and the other one for block B. And we can also have a coordinate system. Let's see if this one is allowing me to rotate it. It does, great. So now I have this block A. The forces on it are MAG. There is a normal reaction from B on A, which we can call N number 1. If A is pulling on B, right, B is going to move under A to the right side while A is still stationary. So the relative direction of motion is going to be, for B, is going to be to the right. So the friction applied to B is going to be on the left. But that friction on B, which is to the left side, has its own reaction on A to the right side. So the direction of friction on block A is going to be to the right, and I call that F1. The reaction to this N1 is also applied downward on block B. So F1 and N1 here and here are action and reaction. We have, of course, mass of B. We have a normal reaction from the ground. We can call it N2. And since the direction of a slide between B and the ground is to the right, so friction for that is also going to be to the left, and we call that F2. So these are the FBDs for the two blocks that we have. And we are going to use a coordinate system, as I said. And this coordinate system is going to be the traditional XY in this case. We can have Z out of the plane toward us as well. So we use Cartesian coordinates. And if you notice here, I did not replace F1 and F2 with any of the mu's times the n's. So I did not say F1 is mu K or mu S times N, or the same thing for F2. So because we don't know, first of all, whether the two blocks move at all, if, let's say for case A, we apply 200 Newton. And if they do, then which one is going to slide with respect to which? Okay, and mu S times N is only a capacity of friction. It's not going to be replacing F1 and F2 at all times. If these are stationary or static friction, there is no formula for them, you know. Please watch my video on static friction. We only can find them through equations of equilibrium. So right now, this F1 and F2 can be considered as two extra unknowns. Of course, we have too many unknowns we cannot solve. But the first question is, what's going to happen between B and the ground? Is B going to move on the ground or not? Or if A and B together, they are going to move on the ground or not? So since we are interested in the reaction on this contact area, and that depends on force N2, and if you look at these two FBDs, clearly in the y direction there is no motion, so N1 is going to be equal to MAG, and N2 is going to be equal to what? N1 plus MBG, so N2 is going to be the sum of the two weights, MAG plus MBG. Right? So it's N2 that is going to determine whether, basically based on the mu s and the mu k that you have and the f that you have, is there going to be any motion or not? So here, this is what we do. Instead of first focusing on each one of the FBDs, I also draw a combined FBD. Okay, so I draw a combined FBD. And on this combined FBD, the advantage is when you combine these two together, basically, the action and the reaction forces N1, F1 on both sides are going to go away. So all you will end up with is MAG, MBG, N2, and the friction F2. Right? Those actions and reactions F1 and N1, they're going to be eliminated once you add them together. Now this is a little bit better. It has only unknown F2 and N2 in it. Okay, so now first I focus on this guy. And I say, well, I have two equations for this. Summation of the forces along x direction is equal to negative, and of course the capital F. We just forgot capital F in both cases. Okay, so this is block B and this is block A. And here we are solving part A. Okay, where F is 200 Newton. So along the x direction, you have capital F minus friction F2. This is equal to mass of block B plus mass of block A, correct, times the common acceleration if they move together. In the y direction, I have what? I have N2 minus MAG minus MBG is equal to, again, the total mass, combined mass, times the acceleration, but this time y direction. So here, assume that like the two blocks are welded together, are glued together. So they do move together, so the acceleration terms are the same, and instead of two blocks, I have one block with the total mass of MA plus MB. Clearly, there is no force in the vertical direction to cause any vertical motion, so AY is going to be 0, and as I said, that means your N2 is going to be equal to the total mass times G, which I have calculated already, and the number for it is 441.45 Newton. So this is the normal reaction on the combined system. Good. Now, the question is this. If I want to have any motion, since the system is starting at rest, so I need a positive AX for the system to move. It means the total force should be positive or should be to the right side, which means F has to be bigger than F2. So if I want any motion, right, if there is any sliding, let me type it here. If there is any sliding between the combined system and the ground, we should have what? As I said, we should have the F force should be bigger than F2. Good. F is 200. What about F2? F2, we don't know whether there is any sliding or not, but we know the max friction that any surface can generate, the Coulombic friction, in general, the max should be what? Mu s times n. So when we say F is bigger than F2 means bigger than any possible scenario of friction that the surface can generate. So it should be bigger than F2 actually what? F2 max. And F2 max is what? Mu s times n, and here n is n2. So I plug in this n2 into this number, and mu s here is 0.4 as the problem is saying. So it has to be bigger than 0.4 times that 400, which you calculate, you will get 176.58 Newton. So as long as the applied force F is bigger than the maximum friction that the surface can potentially generate, which is 176.58, there will be a sliding, there will be a motion, and my force is 200, already bigger than that. So there is definitely what? There will be sliding. Now, if there is sliding, what does it mean about F2? If there is a sliding, means F2 is going to be kinetic friction. So your F2 now can be calculated as what? Mu k times n2, correct? Because it's kinetic friction, there is a sliding. So the actual amount of friction is going to be n, which is this number, times mu k, which is 0.35, so it's a little bit less than mu s. And if we do this number, that's 154.55. So this is the friction that the system will be exposed to between the system and the ground. Good? Fine. If I have that number and I go and plug it back into this equation number 1, so I call this equation 1, and I plug this into 1. Since I have F2 as a number, and I have F as a number, and I have MA plus MB as a number, the only unknown in it is going to be what? AX. So if I calculate that, your AX of the combined system is going to be 200 minus this number divided by total mass, which is 45 kilogram. Correct? So let's get that number. So here we go. 200 minus answer divided by 45, and the number is going to be 1.01. So it is 1.01 units meters per second squared. So if you can keep them together, that's the amount of friction, and this is the common acceleration, if you can. Now the question is this: can you keep them together? Can you have enough of friction between block A and B so that they move together? We have to figure that out. So now, since I need to focus on individual blocks, I need to go back to the individual FBDs. So now, if I focus on block A, for this block A, I have two equations. Sum of the forces in the x direction is equal to F1. This is equal to mass A times acceleration AX. And sum of the forces y is equal to N1 minus MAG equals mass A times acceleration of AY. Again, on y there is no external vertical force that wants to move it upward, so there will be no acceleration. Therefore, your N1 is going to be equal to MAG, and that is going to be 15 times 9.81, 147.15. Now, under what condition do I have both blocks moving together? Is that going to happen here? So, if I bring the acceleration that I found from the last stage here, 1.01, which is the common joint velocity if both of them move together. If I bring that and plug it here, right, because when they move together, they both have the same acceleration. So if I plug that number here, 1.01, and MA was 15, the number that I need, the friction that I need to make it happen is going to be what? You multiply them together, you get 15.15 Newton. Okay, this is the amount of friction that you need. How much is the maximum friction that you can have between A and B? The F1 max is how much? At max, it can be mu s times n1. Mu s is 0.4. That is your n. If you multiply n by mu s, correct? So multiply this answer by 0.4, you will get 5886. So the surface between A and B can generate friction up to about 59 newtons. But all you need is only 15 newtons, which is what? This is way bigger than what you need. So your surface is well capable of creating that friction. And that means the answer is yes. The two blocks can stick together, can stay together, because the friction that I need for it to happen is well below the capacity of the friction of the surfaces. Okay, so for this reason, it means there is what? That block A and B can move together without sliding. If I got a number that was bigger than mu s times n, means the surface cannot generate that amount of friction to give a block A the sufficient acceleration. That means yes, there will be sliding. A will be falling behind. But now you see that's way below my capacity, so the answer is yes, I can do that. Good. So now you can see that in this case, block B moves on the ground, and between A and B is not going to be any sliding, so A will be dragged with B to the right side without any sliding with respect to B. So in this case, how much is acceleration of A and B? Both of them are equal to this number. Okay, this is A of x for both A and B, right? The friction between B and ground is going to be kinetic, between A and B is going to be static. Now the question is, how much is this F1? If somebody asks you how much is F1, of course F1 is not going to be equal to this mu s times n. This mu s times n is just the capacity, the max friction. So how much F1 do you need? Just this much. Just this much to give it what? The same acceleration as everything else. So how do I find F1? I find it through the equation of motion. I'm not, because F1 is a static friction. That's the biggest mistake I see my students make. Whenever it's a static friction, they immediately replace it with mu s times n. Mu s times n is only on the very edge of sliding. When there is no sliding, when you don't need maximum friction of the surface, it's a static friction. There is no formula for it. The only way to find it is through what? The equations of motion. So F1 here is 50 Newton, not 58. Good? So that's part A. Now what changes in part B? So if I want to solve part B, every calculation could be quite similar, except what? N2 is still the sum of the weights, no problem. F this time is now what? It is 400, which is way bigger than the max friction that between the ground and block B can be generated, 176. So of course it will move, right? And again, the kinetic friction that exists between B and the ground is going to be mu k times n. It's going to be the same number. What's the only difference? The only difference is A. A is this time the difference between 400 and this friction, not 200 and this friction. So you have to subtract this number from 400 and divide it by 45 kilogram to get A. So in this case, your A is going to be quite larger, right? So this time here, when you do that 154, now you subtract 400 from that and divide by 45, and the answer is 546, correct? So the acceleration this time is going to be 5.46 meters per second. Now, if I want A and B to move together, I go back and look at block A again. The maximum friction that exists between A and B is still the same. Mu s is the same, N1, which is the weight of block A, is the same. So the max friction that you can generate is still 58. But how much do you need? This time you have to replace this 1.01 by how much? By 546. And if you replace that by 546, the amount of friction that you get from this top equation is going to be 8183. Okay? And this 8183 is definitely bigger than the maximum friction that you can generate. So there is no way your surface between A and B can generate that required friction. When that happens, it means block A and B what? Will slide with respect to each other. With respect to each other. If that is the case, means F1 is going to be kinetic friction. So F1 is going to be mu k times N1. And so I need to multiply that N1 by mu k, which is 0.35. So we need to multiply 147.15 by how much? 0.35. So 5150. This is the amount of friction that will be standing in front of B to move, and that is the amount of friction that will move A to the right. So now that you know how much friction you have, now you are going to plug it back here. The amount of friction is going to be 5150. And with that mass, that can give you what? A corresponding acceleration. And how much is that acceleration? Well, we are going to find it. A of AX, let's find it. Divide that force by 15. correct? Which is going to be 3.43 meters per second squared. So this is the acceleration of block A. Clearly, you see it is less than the common acceleration. Definitely, it is less than the common acceleration, 5.46. Right? It's less than that, so there is definitely going to be sliding. But now the question is, how much is A of B now? Is that going to be that number, 5.46? The answer is no. That is not going to be A of B. This is actually, if you really want it, it's the A of the centroid of the system. It's not A of B. It's the A of the combined mass, right? It's E of the combined mass. It's E of the whole, A of the whole system, A of the center of mass of the system. So that's not A of block B. A of block A is 3.43. How much is A of B? I have to go and look at what? Look at the FBD of block B. So I need to basically make a copy of this, right? And go down here. And take a look, see what's going to happen. So this is block B. Now for block B, I need to look at the x direction. Some forces in the x is F minus F1 minus F2. This is equal to mass B times acceleration Bx. F is 400. F1, we found it. It is 5150. F2, we also found. It is 154.51. M of block B is 30 kilogram. That means acceleration B of x is going to be, so let's do it, 400 minus 5150 minus 154.51. Divided by 30, 6.47. You see? So A of B is not going to be this number that you found, 546. That's not A of B. A of B is more than that. A of A was less than that, if you remember, right? If we look up here, it was 343. So that's A of A. This is A of B for problem case 2. The A of the centroid is somewhere between these two. How can I find it? You might say, what's the relation between these two A's and that one? Well, as I said, this number is A of the centroid. And you know A of the centroid is what? For a system with two masses. It is going to be M1, A1 plus M2, B2 divided by what? The total mass. Correct? That's what it is. So if we plug in these numbers, correct? This one is 15, this one is 3.43, this one is 6.47, and this one is, or no, the other one is 6.47, this is 30. And this whole mass is 45. Will I get that number? Well, we can check it. So 15, 3.43 plus 30 times 6.47 divided by 45. Look at the number, 546, which is what you had over here. Okay, so don't be tricked to say that's acceleration of B. No, acceleration of B is more. And you might say now, could I have found acceleration of b through this number? For sure. I did not need to go to FBD of b to find a of b. I could find this a of b without even going to FBD of block b, right? I could have plugged this number in here and say, well, I don't know a of b, correct? And then solve for what? For a of b. So if here you solve for a of b, you would have been finding this number. Okay, so I don't need to go over all three FBDs. Once I can find the common acceleration, the acceleration of the centroid from the the joint FBD, and I go to FBD number 1 to find acceleration of 1, I can find the other one through this formula. And the reason is your three FBDs are not independent. The last one is made by adding the first two. So it's not like you can get separate numbers. What number you get from two of them is the number that you get from a third one. And one more, okay? So you only have two FBDs, and that's all you need to solve these problems, right? And this is how you approach this problem for case A and case B. I hope it was useful to you. See you with my next video on the next problem.